All right. Let's see. So today's class is not supposed to be that easy. We'll have to go a little slower than normal just to make sure we're on the same page. What's difficult about it is that we're going to be talking about things that you're not really used to. This is a little, here is where the class takes veers away from physics 50. Well, circuits is already different, but you know, those are rules. Here, you're talking about forces, you think you know it, but actually this is different from physics 50 because magnetic forces don't work the same way as gravity in important ways, also not like electric fields either. Sorry, one second. So we'll go, I'll try to go slowly, and as usual, it's better if we get it now instead of postponing it for later, trying to figure out. So this is the business about the right-hand rule. And unfortunately, I'll just follow the PowerPoint here because of the drawings in the PowerPoint. When I do the right-hand rule here, Well, actually, my hand doesn't seem to be disappearing now. I don't know. Sometimes it disappears from view, sometimes it doesn't. So it's a little hard for you to see my right-hand rule business on online. It's easier in person for sure. So I'll follow the PowerPoint. We've practiced already the right-hand rules, but we're definitely gonna need them now. And you have to keep it, just always be comfortable with it because you're not used to this. Okay, so it's not that it's super hard, but usually, but there are several things that are not the same. I'll give examples as I go along, and as usual, I'll give you guidance about the problems that are going to show up in the exam about this. But yeah, this is a little bit different in several respects. Let me start with one. There's other ways in which this is different. You'll see today we're going to do several things that are not stuff you're used to from the past. The first one I would say is the fact that when you have a magnetic force, we're going to see in a second that the magnetic field and the force don't point in the same direction. That's not what you're used to, right? If I say the acceleration of gravity and the force of gravity, of course they point in the same direction. If I say the electric field, if you know the direction of the electric field, then you know the direction of the force. It could be a minus if it's an electron, then it turns out to be down instead of up. But you're still, the direction, the sense of the force, you still, just by looking at the electric field, you get the sense of the force. To within a minus sign, it could be up, could be down. But here, the force and the field are perpendicular to each other. So the force of the force produced by magnetic fields are not in the direction of the magnetic field. They're perpendicular. So you're not used to that. So that will, you just got to keep it in mind. It's not that it's super tough, but you just got to keep it in mind, and it has very important consequences that I will show you in a second. Okay, now let me I wrote a note here. I would like to keep it practical, as I always do, just give you examples that are very likely or guaranteed to show up in the exam. So there are two such examples that I'm going to cover today. One is an electron in a magnetic field, an external magnetic field. And then this one is a little bit more interesting. Let me talk about this a little bit, and I'm just telling you what the problem is in advance, okay? But of course, you're not ready for it yet. I'm just letting you know, okay, here's what's coming. This is a little different than the stuff you're used to, and you have to think of all the pieces that go into this, and then you keep it in mind, and then later on you'll see what I mean, and you'll fill up all the pieces, and everything will be a little clearer. But I'm just letting you know the problem in advance, so you can keep it in your head a little bit as we talk about things. So here's a problem just to keep in mind. You have two protons, right? And so far, we've been talking about what we like to call electrostatics. So that means the charges are not moving around. They're just sitting there, and then you can calculate the electric field of the charge, and you could calculate the forces. And all that seems in the end like, okay, well, that's not so bad. So if I have two protons, I know the force between them, and it's kq squared over r squared. And they're two protons I'm talking about right now. Okay, that's great. That's the electric force. Okay, now we're going to talk about the magnetic force. Well, actually, it turns out that it's interesting because you can have an external field. You have an external field. And if you have, that's the first part we're going to do. You start out, somehow there is an external field in some location. So there's a magnet. There's a big magnet, and then you shoot a proton through the magnet. When there's a moving particle in a magnetic field, there is a force, an additional force. We call that the magnetic force. Okay, but this situation is a little bit more complicated because moving charges themselves produce magnetic fields. So that's new. You haven't heard of that before. Maybe you heard about this field and you already know that fact, but that's not really used in physics 50 at all. Okay, so if a mass is moving along, that doesn't mean that it creates a gravitational field. It has, So here, that's what will happen. So I will make it a little extra hard on top of it. So you have a proton. So now we have 2 protons. So this is what I mean by this. You have 2 protons. There's, of course, the electric force. That's always there. But now there is going to be actually a magnetic force between the protons. So why is that? Well, in the first part, we will cover the fact that a moving charge in a magnetic field suffers a force or feels a force. Okay, but actually what's interesting here is that the other proton is the thing that produces the field. So that has 2 pieces to it. So we'll start with one piece, and then very soon after that, we're going to do the other piece. So the first piece is a charge moving in a magnetic field. That's the first piece. The second piece is a moving charge produces a magnetic field. So those are 2 distinct pieces that are happening here. Okay. The bottom line in the end is because of those 2 pieces, when you add them all together, what will happen is that these 2 protons, when they're moving, have a magnetic force that counters the electric force, that fights the electric force. And we will get more into the details. We'll solve this problem in detail once you know the formulas, of course, and how to apply them. You know how to solve this. But to solve this problem, again, you need two. So one question that could arise, and that's the one that, is it possible for the magnetic force to cancel out the electric force? We'll find out that's impossible, because for that to happen, the protons will have to be moving at the speed of light. But nothing that has mass can travel at the speed of light. But that's interesting, because in this force already, the speed of light shows up already. So now you start to have to think about light and magnetic forces and electric fields and magnetic fields, and then eventually you find out much later, and we're not really going to get to it, that they're related. Okay, so that there is definitely a connection there. Anyway, so yes, to solve this problem of 2 protons moving, so if they're at rest, then, so it's electrostatics, then you just have the electric field, you're done. But once the protons are moving, then a new force shows up, this magnetic force. And as I said, that has 2 pieces. Okay, so let's start with the first piece. But then you have to realize that very quickly there's this other piece that is quite abstract, shows up. Okay, so you won't be able, from my first piece, you won't have the answer yet. So it might be still a little confusing. You got to get to the second part. And then when you put the 2 together, then sure, you can tackle this problem. Okay. Okay, so we start with the first piece. Well, this part is about the forces between poles. Let me not get into this part so much. I want to, as usual, focus a little bit more on the practical stuff. Magnetic poles are very interested in physics. And I'll just mention that something that they say here, and it's definitely true, that magnets look a little bit like they're talking the same thing as charges. Actually, it's not quite the same thing. It's similar to charges, but magnetic poles are not really charges. Because when you have charges, you can have a positive charge by itself, and you can have a negative charge by itself. You have a box, and inside the box, you have a negative charge. And that's it. Nothing else, just a negative charge sitting there. It turns out with poles, with magnets, it doesn't work that way. If you have and this is actually a very deep comment of physics that I'm not going to get into, and people try to find explanations for it. Believe it or not, they try in the universe why this is the case. But it turns out that there are no single poles. So you cannot have a north pole by itself or a south pole by itself. And they have theories out there about why that is, involving the Big Bang and all kinds of things like that. So we're not going to discuss that. We're just going to say, okay, great. Poles are a little bit different from charges. So it turns out that for that reason, we're not really going to have a Gauss's law for magnets. Not because you couldn't write one. You could write a Gauss's law for magnets. But since poles come in pairs, then a Gauss's law for magnets will not help you, because the enclosed charge, so to speak, in this case, the enclosed poles, would always be 0 because they have the north and the south together. So anyway, there's a little bit of theory going on already about the speed of light and about poles, magnetic poles, and all kinds of things like that that people think about at pretty deep levels. We're not going to get into that. We're just going to take the few basic facts that we know, and then you'll see that it shows up though later on. Okay, so even though I go through it very fast right now, the fact that there are no individual separated magnetic poles north and south does have consequences later on, and this PowerPoint will end up going in a different direction for that reason. It won't be like the charge, like the other one where you just have charges. Okay. Now we're going to have to discuss what a magnet, a pole is, and it turns out that this is again you can describe everything in terms of moving charges. That's a little premature. That comes later. So at this point, this should be a little mysterious. What the hell is going on here? We're going to demystify it a little bit, but there's still some things that are not mysterious. People have theories, but they're pretty deep about this stuff. So here's what they're trying to tell you about. This is what I was saying before about the magnetic monopoles not being possible. So they're saying the same thing, that you might think that you could separate poles just by breaking magnets or whatever. It turns out that you cannot do it. Okay, so let's not get into that too much. What we need to know is just this magnetic force. How does it work? Okay, so that's where immediately we're going to use the right-hand rule. And I'll just use the PowerPoint to illustrate that. And I will tell you the consequences of the force law that we're creating. Okay, so we start right with that. Okay, so we're going to do a cross product. So we start by saying, okay, great. If I take this cross product, so the magnetic force of a moving charge is Q, the velocity vector V, and then cross the B field, B. So immediately they're telling you, because there is a cross product in there, you gotta remember that the cross product has a sign of the angle. So when you're taking cross product, you gotta do the right order. You gotta say the velocity cross to the magnetic field. That's not the same thing as the magnetic field cross the velocities with a minus sign. That would be. Okay, so the order matters. So it's velocity first, then cross the B field, and then we'll use the right-hand rule to do that. So immediately, if the velocity and the magnetic field are aligned, then there is no force. Okay, so that's not too tough. Now, one very important thing, I wrote something here down. I'm not going to spend too much time on it, but it's a very important thing. It's kind of like this one, actually, we can cover. We can discuss it. It's not one of those things that's super theoretical that I have to talk about the Big Bang to tell you about the ideas that people have about that. That's not quite like that. But it turns out it's a little surprising that when you have, and this is very important for us, for any electrical engineer or anybody at this level, even at this level, this is kind of surprising. And of course, it has explanations and there are ways around it. But first, you got to make sure that you understand the statement is exact. Given our force law we just wrote, Q, V crossed B field, from that force law, I can prove, and I prove it here very simply, but let me just talk about it, that the magnetic force cannot do work. Okay, we haven't been talking about a lot about calculation of work. We've described it more about energy. But you have to remember that, of course, when you're talking about conservation of energy, you're talking about work. So if you're saying work increases the kinetic energy, work done by the field increases the kinetic energy of the particle. Okay, great. So this force we just wrote down cannot change the kinetic energy of the particle. That's surprising, because many, many times you can do things with magnets, make the start off currents and all kinds of things, which seem to violate this statement I just made, that the magnetic force cannot do work. Okay, so let me just, even though it's a little premature, let me give you the answer to that actually. right now, because I don't want to leave it here like a big mystery that nobody understands. And so therefore, we're never going to get to it. No, this one is easy to understand how you can get around it. But you still have to think about it, but it's not like a big mystery. So what's happening here is this. We wrote down an expression for the force, okay? Now, based on that expression for the force, this is what we can do. We can define work as F dot dx. That's the definition of work. Is the force dotted? There is a dot product in there. You need the dot product. Dot product means there is a cosine. This is stuff from Physics 50, actually. You were doing this for gravity. Just, this is a general definition for the work done by the force that you're talking about, whether it's the gravity force or the electric force or the magnetic force, in this case. Okay, so to calculate the work, we have to do F dot dx. That's the definition. Then what we can do is we can rewrite the dx as dx dt times dt, because you would just cancel the dt's. Of course, you can rewrite that dx in that form. But actually, when you write it in that form, you can see that dx dt is the same thing as speed, the speed of the particle. Dx dt with a vector sign is the speed. So that means that my definition for work, instead of writing it as F dot dx, and it's the same thing, I can say F dot velocity times dt. So now I'm dotting the force into the velocity. But from the definition of the force and the cross product, this is something that you definitely need to know and keep in mind, that if I make this the definition, then the force is perpendicular to both that and that. So that's the right-hand rule. It's implicit in the right-hand rule. You take velocity, you take the B field, and then the thumb, which is perpendicular to both the velocity and the B field, is the force. My thumb points in the direction of the force. So the force is perpendicular to my velocity vector, and the force is also perpendicular to the B field, by definition, based on the formula. Okay. Well, the thing is, there is a dot product in there. So if I take the force, which is perpendicular to the velocity, and I dot it into the velocity, since one is perpendicular to the other, that must be zero. Okay, so I just proved that, right? In 2 seconds, you could do it more. Of course, you could write vectors in general form and prove it, with dotting everything. But basically, you would be doing the same thing I just did in this little notation. And what that means is, there's no flaw in this argument. The magnetic force cannot do work, period. That's it, you're done. However, actually, it turns out that there is a loophole that so you shouldn't let this confuse you, because later on, it seems like magnetic fields will increase they will create currents, for instance. We'll talk about that later. So if a magnetic field can create currents, isn't that making particles move? Isn't that changing their kinetic energy? The answer is yes. And here is the loophole, and then we'll get back to it when it comes. Okay, but this is a weird thing about this force. Even though the magnetic force can't do work, what ends up happening is a changing magnetic field produces an electric field. And electric fields have no trouble doing work. So it's like the magnetic field has found a loophole, a workaround. It itself cannot do work directly, but if you change it around, then it will produce an electric field, and the electric field will do work just fine. So that means that what comes later is not really in contradiction to what I just said, that a magnetic force cannot do work. Okay, so that confuses people sometimes, because at one point you're saying it cannot do work, and later on we're talking about magnetic fields producing currents. There is actually no contradiction, but you do have to think about that a little bit. What happened? How did that work out? Okay, we'll come back to it, but but nevertheless, what I just said is definitely true, and there's nothing wrong with it. So since the work is zero, that means this. Let's make sure you understand that. Make sure. Based on what we're going to see right now, the kinetic energy of the particle in the magnetic field cannot change because the magnetic force cannot change the kinetic energy of the particle. Okay, because it doesn't do work. You'll see that in a practical example in a second. And when I come to it, I'll tell you, look, we just satisfied this condition. We are doing a force, we have a force, and things are happening, but the kinetic energy is not changing. Okay, so you'll see that. I'm gonna set up a very specific case where you just have a magnetic field, you have a particle moving in circles. And there will be a force, of course, but the kinetic energy of the particle will not change because the magnetic force cannot do work. Okay, so you'll see that happening in practice in a second. At this point, it sounds theoretical. It's not. We're going to apply it immediately. Okay. Well, this is more the same. We're going to use it in cases here. Let's see the first case we have here going on. Let me, 1 second. I'm trying to remember. Oh, yeah, I remember which cases we have to be in. Okay. So, so we're going to use it. I'll go to the case of the let's try to cover. We may be able to cover this entire PowerPoint just today, but let's be practical as soon as we can. And so one of the cases, they have here a thing where they have two plates. They have a magnetic field and they also have an electric field. That's one case that we can cover. That's also in the mastering physics problems. We should cover that. Then the other one is a particle moving in a magnetic field. We should cover that as well. Okay, but yeah, you're gonna have to use the right-hand rule. So let's get started on that already. Okay, so basically, I don't know exactly what best way to use this. We've done this already. You guys seem to do okay. But we'll see. We'll test it out for you. I'll give examples of wires in magnetic fields to see what we can come up with. But in any case, let's remind ourselves of this right-hand rule. By the way, one of the professors at San Jose State has an app that he wants others to use. So I'm going to give it a try. I'll pass it along to you guys. It's an app designed for this kind of a problem, so you can visualize things. I'm not sure if it's going to be helpful or not because I've never used it. He's doing a sabbatical and he is working on this, trying to do some apps for students and things. So I haven't tried it out yet, but I'll pass it along to you guys and see if it helps you. I don't know exactly how helpful it's going to be. But in any case, so the right-hand rule thing. So we start out with, remember how it works. You do your fingers, you point it in the direction of the velocity vector. So in that case, it's like this. Well, you can't see very well already. Yeah, I'm already having trouble showing this. My hand disappears. But it's going like this. Let's try like that. And then you cross into the B field like that. And then my thumb points in the direction of the force. Okay, so in this case, based on how I'm looking at I can look at the screen. Let's assume I'm looking at the screen and you're looking at the screen. So I would be velocity, B field to my right, and then the force is up. Okay, so now it's a right angle. This is a 3D thing, right? So the force is perpendicular to the magnetic field and also perpendicular to the velocity, perpendicular to both. Okay? Okay, let's see if we can figure this out. Okay, well, there's more examples of the right-hand rule. More examples of the right-hand rule. Let's get practical here. Here they're trying to tell you, what is this trying to tell you? Okay, so here, yeah, let's just very briefly say what they're trying to say here, just to make us sure. So it's just the right-hand rule. We'll give it a practice. So far it's been the right-hand rule, right-hand rule. Right here, they're trying to tell you what I said at first, that the force is not pointed into the magnetic, so the magnetic field line is to the right in the plane, and the force is perpendicular to that. So remember when we did this, if we write in the electric field, well, there's a Q in there, but the force and the electric field are in the same direction. If there is a minus, then anti, but here is different. So that's a little confusing. That's what I said at the beginning. So that's not, shouldn't be surprised by now. Well, they have this here. Okay, since they have this here, let me talk about it. But I don't agree with this placement here. Okay, all of a sudden, so right now they were talking about the force on a charge. So you have an external field, and a field that you didn't talk about how it was produced. You just put a magnet in there. You don't worry about it just yet. And then you'd make the charge move around in that magnetic field, and then you find out that there's this force, which is Q velocity cross B. Now here they're saying, wow, this is a different factoid. It's not really related to what we were just talking about. So this is too much of a jump, in my opinion. I don't like how the format of this PowerPoint. But here they're saying, how would you produce a magnetic field? Well, it turns out that a wire carrying a current will produce a magnetic field. Okay, so it's actually, you don't even need a wire, just the moving charges. Moving charges will produce a magnetic field. So that here they're telling you how it was the magnetic field produced in the first place. That's kind of like mixing things. I would like to just continue talking for a little bit. We're not there yet. We're not really ready to go to the next step. We will still need to continue to talk about what happens when a charge moves in an external magnetic field without worrying about how was the magnetic field produced yet. Okay, so let's postpone this PowerPoint slide. I don't like it here. And go back to figure out, well, here they're telling you about the Gauss's law for magnets. Actually, let's just do practical. Here you go. That's this is what we need to do. Now, let me get out of here. Just gives the answer. This you need, okay? So we're gonna cover two cases, and I would like you to tell me, let's set it up without looking at the PowerPoint. That gives you the answers. Let's give two examples already. So these are practical examples. So example number one. Okay, so your plate's like a capacitor. Okay, now this example shows up a lot on Master in Physics. So this will help you with Master in Physics. And what you want to do is figure out the directions of the forces. Okay, so this is what I'm gonna do. I'm gonna have the positive plate here. Okay, I'm gonna have a negative plate here. And then I'm gonna have a magnetic field. Now to draw this and without doing a three-dimensional drawing, which I don't know how to do anyway, then I'm gonna use the notation. Let's use a notation that makes things a lot easier to do drawings, which is this notation. A vector that's coming out of the screen, people like to draw that as this kind of a symbol. So this is kind of like you're seeing an arrow and you're seeing the tip of the arrow coming your way to your eyes. So then they say, okay, that's something coming out of the computer screen. So that would be this. So if I draw this, if I say that's my B field, that means my B field is coming out of the computer screen at me. If I do this, this is kind of like seeing the feathers of the arrow. I think that's how this originated. So if I do a cross, that means a B field moving into the computer screen. Okay? So let's do the moving. So people like to do diagrams that look like this then, because what they mean by this is that the magnetic field points into the computer screen. Okay, so let's see how would we do it. Let's see what direction these forces are. Great. So now suppose I have an electron. I have an electron, and I shoot the electron that way. Okay, that's an electron. So it's a negative charge. So let's see if we figure out using our rules from before. So there are two forces. So there's the electric force, and then there is the magnetic force. And we want to know in what direction. So again, we're not worried at this point. Notice, how did you generate the magnetic force, the magnetic field? I didn't tell you how I generated the magnetic field. All I said is this is an external magnetic field is present here, and it points into the computer screen. That's it. The next step is, well, how the hell did you do that? Okay, so there are ways to do that. Okay, but that's premature. We're not ready for that. I'm not sure why they stuck it in there. Okay, so force, and then you have Q, V, cross B. Okay, so let's see if we apply these rules correctly. In what direction is this force? So it would be either to the right or to the left. So which one do you say? You need the directions. Remember, there are sign rules that we're using here. How are we doing with people here today? A little light. This is kind of hard material. This is going to show up in the exam for sure. I'll tell you the specific problems, but there will be a bunch of multiple choice problems where you still have to do the right-hand rule. Anyway, in which direction is the electric field here? Up, down, left, or right? Can somebody put it in chat? Trent says to the right. Does everybody agree with to the right? Ryan says left. Okay, let's remember how this goes. Oh, what? Ryan, you doubted yourself too quickly, I think. How did this go? So the electric force points from the positive to the negative. Okay, no, Ryan, you had said it right. So, okay, so the direction of the motion of the electron, I said, is I started down. So that's the initial, and now let's see if we can keep it in that moving down without any, but right now the initial movement is down. Okay, now I'm not asking about the velocity. Velocity, I take an electron gun, I shoot the electron straight down. Now what I want to know is what are the forces on this electron? Okay, so remember how this works. The electric field points from the plus plate to the minus plate, correct? Everybody agree with that? Here is the electric field. Points like that. Is that true? Right? So then to get the force, I take the charge and I multiply by the electric field. In what direction is the force? Right. Correct. You gotta please keep that in mind. That's the thing that does make a lot of people lose points in this next exam. You always gotta keep in mind, people like to do different things. I'm not sure what to tell you to do. I'm not really sure what's best. What I like to do is I just keep my right hand rule. I see that people start using the left hand when they're talking about negative charges. I don't like to do that. I just say, okay, I'll do everything with my right hand. And then remember that this is a negative charge, and so you gotta reverse the direction of the force. You can't keep the same direction of the force. So because the force has a Q in front of, you see there's a Q right for both of them. So since we're talking about an electron, then you gotta flip it. Okay, so I would just keep using the right hand rule for the B field, but then flip it when it comes down to the direction of the force because there are Q's in front. Okay? Anyway, the electric field is to the right, so the force is to the left. The electric force is to the left. Agreed? Are we together on that one? Okay. How about this one? What direction is that? I'll give a hint. Is it right or left? None. Well, I'm not trying to be tricky. I'm giving you a hint. You can choose to the right or you can choose to the left for the magnetic. So I have an initial velocity. So it's an electron, and I shoot it down, so it does have an initial velocity. Okay, I wasn't trying to be super tricky, no. You gotta choose left or right. What would you like to choose? And again, you need to know how to do this. Yes, you can't. You're gonna do this a bunch of times. Now, eventually, some people practice it enough. It's not really that hard. But if you don't practice it, then yeah. Okay, let's do it together, okay? I'm gonna, tell me if I'm doing the right thing. So I do my right hand rule. I'm using my right hand. So this is how I like to do it. I always just stick using the right hand rule. Never use the left hand for anything. And then just remember that if you have a negative charge, you gotta flip it. At the last moment, you flip it. Whatever you got, you're just gonna have to flip because it's a negative charge. Okay, so what do? To calculate, to use the right hand rule, I get my fingers in the direction of the velocity. The velocity is down, agreed? So I'm doing the velocity down. Now, the B field is into the computer screen. So like that. So what direction does my thumb point? To my right, right? But then it's a negative charge. So I gotta flip it. It's to the left again. Okay, great. So you see, I mean, let's please everybody notice what's happening. Everybody has to go through the same process. You cannot keep making the same mistakes. Eventually, of course, you realize what the mistake is and it's no big deal, then you fix it. But you gotta try to make sure every time that you don't let it pass, just get it every time. Don't, if you start letting it pass, then you're gonna start thinking about it in the exam. Well, as you know now, there is not a lot of time in the exam. You gotta figure it out before the exam. Okay, so it's down this way to the right, and then you flip it to the left. Okay, so in this situation, the electric field and the magnetic field are in the same direction. Okay, now what I could do is I could erase the B field here and make it go out instead. So it would be like this, and then I would have a B field like that. Okay. In this case, this would be to the left still, nothing changed there. But now this one would be to the right. Okay? If anybody disagrees, let me know, okay? Please don't let this, that's why I'm going so slow. We're gonna use this for something. Okay. So now suppose I say, okay, how about if I try to make the two cancel each other out? Is that possible? Can I do that? Well, yeah, since one is to the right, the other one is to the left in this setup. The B field is coming out. So then again, I would have to do, that's why it's hard. I still have to use my right hand. So the velocity is going down. The B field is coming out of the computer screen. Now this is to the left here. But now I flip it, now it's to the right. Okay, great. So now they're fighting each other. Yeah, sure, I can repeat it. Okay, I was just trying to repeat it, but I gotta go like this. Okay, I'll still look at you, otherwise I'm gonna get you confused. So I can do this right in front of my body and my hands won't disappear, I guess. So I'm pointing my fingers down. So I need to start with the velocity of the particle. That's the first thing in the cross product. I'm just doing the cross product when I'm using the right hand rule. So the velocity is down. We can agree on that. I'm shooting an electron down. Then I cross my fingers into the magnetic field. So for this drawing, the magnetic field is coming out of the computer. So when I curl my fingers, I have to now curl my fingers into the direction of the magnetic field, which is so it's that way. Now I have my fingers out of the computer screen. And then my thumb points in the direction of the force. That would be to the left, sorry. But the thing is, this is an electron. So now we have to get to that Q in there. We never did that. So since when I'm doing the right-hand rule, I'm just doing the cross part, this part, the cross. But now because it's an electron, I have to flip it. And that's how it becomes to the right, to this, in that direction. Maninder, how is that? Is it tough to see me doing this in the computer screen? Probably. Let me rewrite this. Does that make sense? Again, you first start by ignoring the sign of the charge. You use your right-hand rule. You start with your fingers. Your fingers have to point in the direction of the velocity. Then you curl your fingers, make them point in the direction of the B field. And then your thumb, in that setup, your thumb will point into the direction of the force. And as a last step, now you have to remember the sign of the charge. Since here we're dealing with an electron, then we have to flip the direction of the force. Okay, we're gonna practice this a lot. Actually, in this particular situation, yeah, the mastering physics will help because you gotta keep doing the right-hand rule. Eventually, it's pretty easy. It's a little hard because you gotta keep changing your body depending on what the diagram shows. But eventually, you get used to it, and there's no big deal after that. Anyway, this was a situation in which I'm fighting the left and the right. So now let's try to see, could I keep the electron without a force? So if there is no force, then it would just continue at constant speed doing what it was doing to begin with. So if I'm going to cancel out the forces, that would be to say that QE equals QV cross B. So that cancels out. Now, what is the cross here? Well, the cross is the sign of the angle between the velocity and the B field. What is the angle between the velocity vector and the B field vector? What is that angle? Where is the angle in between equal? Nobody, 90, right? That's right, 90 degrees is correct. The velocity is down and the B field, so it's like down and out of the board. So there's a 90-degree angle because this is a 3D drawing, really. So 90 is correct. So what is the sign of 90? 1. So therefore, I can just get rid of the cross product and just write E equals VB. So the velocity equals E. So what does this mean? So what am I trying to do? I'm trying to do this. If I shoot an electron at the right speed, then it will suffer no force. The two forces will cancel out. And then the electron will move in a straight line right through this instrument. People call this a velocity selector because meaning particles that have the right velocity, they're able to go across without suffering any force. If they have the wrong velocity, they're going to smack into the sides of the instrument, so they're not going to continue. So by the time you check outside of this, you will know what the velocity is of the thing that went across. Okay, so you're selecting particles that have this velocity. The particles that have exactly that velocity can make it through the instrument. Why is this useful? Okay, I'm going to tell you there is something I'm going to tell you a little bit about this. Usually when they start discussing, detailed equipment, I tend to not spend a lot of time, if any, on that. But here is an interesting one. It's very useful, actually. It's called a spectrometer. And I'll tell you how this works. But basically, whenever you want to measure the mass of particles, you're going to have combinations of electric fields and magnetic fields of this sort. I'll be more precise in a second. But this is the instruments. These are the instruments. So, for instance, we sent a spacecraft to Titan. Titan is a moon of Saturn. Turns out Titan is made of methane at the surface, and ethane. And so when people wanted to figure out how do you know that, well, they actually landed something on the moon, and it had these magnetic fields and electric fields. And actually, with this equipment, they can actually measure the mass of the things, the particles that fly through them, through this instrument. So how would you do that? Okay, for that you need two pieces to make that work. You need this velocity selector I just was explaining, and now you need another piece. The other piece is also a practical thing, which is this. Okay, here we have plates, and we have a magnetic field. Now forget the plates. Now suppose here's another thing that another example. So that was example 1. Now, example 2. And you will find this all over again in Master in Physics for sure. This is example 2. In example 2, all we're going to have is a magnetic field in a region of space. And again, I'm not telling you how are we doing with time. Okay, yeah, we have time for this. I'm not telling you what's producing this magnetic field yet. Later, we'll do that, of course. We'll say, okay, in order to produce a magnetic field, you could do it this way or that way or whatever. But right now, somehow there is an external magnetic field, and I have a charge. And let's make this a positive charge. And that's the velocity. So I shoot it. Now, this is it's kind of like the thing above, except I remove the plates. No more plates, no more electric field. Just the magnetic field, that's it. Okay, so my question for you is, based on this drawing, let's see if we get it right this time. We already went through it. Okay, now I made it a little easier because now this is a positive charge, so I don't have to do the final flip or whatever. But what direction? So here is the center of this thing. So, you know, this magnetic field originates from this center here. So here's the charge. In what direction will the force be? Up, down, left, or right on this charge? Please, everybody should try this, okay? It's not... this is the velocity. Let me say that again, okay? See if we all agree. Let's try to all agree. I have a particle, the magnetic field is into the board. My particle is moving straight up at the initial condition. In the initial instance, I shoot the particle up. And I want to know, at that time, when the particle is moving up, in what direction is the magnetic force? Can we get an agreement? Some people say up, and some people say left. Can we agree? I'm hearing more lefts. Okay, great. The lefts have it. That's right. Okay, for the people who said up, no big deal. We're just starting this. The force always has to be perpendicular to both the magnetic field and the velocity. The velocity is up. So the force could not really be up, right? Because that would be parallel. Then the force and the velocity would be parallel to each other. No, it has to be perpendicular to both the velocity and the magnetic field. So it can only be to the left or to the right. So now that's where the right-hand rule comes in. My fingers go in the direction of the velocity, then into the board, then my thumb points into that, so that's left. So that's the direction of the force. That way. That direction is perpendicular to both, okay? So you need to keep that in mind. You can't say it's well-defined. You'll see after you do it a few times, there's no ambiguity here. You have to find the direction that's perpendicular to both. And then the right-hand rule tells you whether it's this way or that way. Basically, a right-hand rule just serves to figure out the sign. Is it to the left or to the right? Well, in this case, it turns out it's to the left. And I'm talking about a positive charge now. Okay, great. So now what we would like to know is what will happen to this particle. So it turns out that there is already, you've already talked about situations like this. This is a situation where the particle will actually, because there is a force of, oh, 1 second, sorry. Okay, yeah, nothing, sorry about that. Because there is a force, the velocity cannot continue in the same direction. Okay, there is a force. So the velocity will start bending. Velocity is a vector. I'm not talking about the speed. So this is a situation, I'm sure you did that in Physics 50. That's one of the Physics 50 topics. Speed is the magnitude. Velocity is the vector. Okay, so the velocity vector changes direction because there is a force. So what is going to happen in this situation is the particle is going to start bending and bending and bending and bending and bending and then come back to where it was. So it's going to move in a circle. And you say, well, at constant speed. And then you say, well, if it's constant speed, there is no acceleration. No, there is acceleration. Remember that stuff from Physics 50? When things move in a circle, there is an acceleration. Can somebody remind me of what it was that, what do you call that acceleration? What? Yeah, centripetal, correct. Centripetal, yes, don't worry about it. Centripetal is fine. I'll type it since, right. Okay, in any case, there is an acceleration. So what does that equal to? What was that acceleration equal to? Can somebody write that down? There was a formula that went with that acceleration. Nobody remembers the formula? For particles moving, right, that's it. Okay? That's the acceleration in that situation. So remember that this is a big sticking point that everybody at first starts thinking the wrong thing. You think that that there is no acceleration, but there is. The speed doesn't change. But what's happening is that the velocity vector keeps changing, keeps changing, keeps changing. And accelerations are the rate of change of the velocity, not the speed. So this is a big thing in Physics 50. You probably spent time on it. Let me just use the formula at this point. Of course, you could rederive the formula and so on. Let's not do that. Let's use it. Okay, that's what we need right now. So you want to use F equals ma. Okay, now what is F? Well, in this case, F is the magnetic force. So we just say, I'm going to drop, well, let's put it with the thing. And what is A? Well, is V squared over R. Now, the thing on the left is a vector though, and that thing is not a vector. I have to put a little R hat to make this work. But actually, let's just forget the vector part because the cross product here is equal to 1 because it's perpendicular again. So I can just write, let me not write it in that way. Let me just write a Q. In this case, I know the directions already. Okay, what is R? This R is the radius of the circle that you're moving in. Okay, so notice one of the speeds cancels out. Okay, so then if you wanna calculate whatever it is that you wanna calculate. Suppose I wanna calculate the radius of the particle. How big a turn does it make? So that would be equal to R equals the mass of the particle. So the bigger the mass, the bigger the radius it makes. So a proton would make a much bigger radius than an electron. An electron would be very tightly following the magnetic field, and a proton would make a bigger orbit. So mv over q, the charge, and then the B field. That's the radius of the orbit. Okay, now for a positive charge, this case, this would be counterclockwise. For a negative charge, it would be clockwise. Now, why is this important? Well, you could put this together with what I just said, but more importantly for our topic, notice at the beginning I told you, okay, I'm going to show you a specific case of something that stays constant, a specific case where the speed does not change, and yet there is a force, so there is no work. Work is the change in kinetic energy. So if I say to you, what is the change in kinetic energy of this particle? Well, kinetic energy is not a vector. There is a change in velocity, that because the acceleration is a vector, but the kinetic energy is not a vector. So if I say, what is the change in kinetic energy of this particle? Obviously, that's zero. The speed is not changing. The kinetic energy of the particle is not changing. It's always the same. So the work done by the force is zero. You see, the work done equals the change in the kinetic energy, right? But the kinetic energy is not increasing or decreasing. So there is no work done, and yet there is a force. How do we know that? By the way, just to make sure, this is also again from Physics 50. How will you know there is a force for sure? Well, if there were no force, then the particle will just continue moving in a straight line. Okay, of course, the thing that makes it turn and turn and turn is the force. This happens all the time with gravity, or if you have a bucket and you put a rope and you make it go around in a circle, then what's happening is the tension of the rope is supplying the force that keeps the thing in orbit, right? So if there were no force, then the thing would just go on a straight line. It wouldn't be turning and turning and turning. So you definitely need a force. Yes. Well, what I meant is that if you want to make the electron, this is the proton, right? So this would be a proton. So for a proton, the force would be to the left. But if instead of a proton here, I had an electron moving up, then the force would be to the right. Okay, and then I would have to draw the diagram the other way. Okay, let's do that. Okay, let me put them side by side. Here's my proton. And here is the initial speed. So then we said that's a proton. So then we said the force is to the left. Always to the it points to the center of the circle. Okay. Now, so basically, as the particle is going up, the force changes its direction and deflects it, moving in the direction of the force. So it's deflecting it to the left. Now, if I did the electron and I have it moving like that, and this is an electron, then the force would be to the right. So it would start, as it start moving up, it would start getting deflected to the right. So it would start turning into that direction like that. And the force would again point towards the center of the circle. So this electron, that's moving around clockwise around the circle. This proton is moving around counterclockwise. What you're assuming, of course, is both have the same direction for the B field. I'm not changing the B field. I'm just changing the sign of the charge. That's it. Right. Right. That's the assumption. Right. I'm just saying, suppose there's I didn't tell you how, you see, again, this is something that bothers people. I think part of the problem is the PowerPoint is a little bit misleading. Forget how we're going to do that next. We're saying there's an external B field everywhere in here. And then I shoot a particle perpendicular to the B field. How will it move? Well, it turns out it moves in circles around the B field. Okay. And in this situation, since the B field is into the board, then the electron would move clockwise and the proton would move counterclockwise. Okay, we can go back to the PowerPoint and you'll see the same things in there. But yeah, this is, now, since I did start with that spectrometer thing, I have a little bit of time. I'm gonna go back to the PowerPoint. The end of the PowerPoint has something that's a little bit tricky. I don't know if I wanna get into that. I'll continue to follow the PowerPoint and then we'll run into something that I may need more time to discuss. So I'll get to it in the next class. But I did try to explain to you this spectrometer. So let me tell you just very briefly, I don't want to spend any time with this. I just want to show you that, yeah, this has a very practical application. What I just discussed has a very practical application, because what I could do is I could combine a velocity selector okay, with And in that case, so basically I could shoot a proton or an electron, it doesn't matter. I shoot a particle this way. And then the second piece, I just have the B field without the plates. And so in the first part, I learned what the velocity of the particle is that crosses my velocity selector. And then it enters the second phase, and there's a master in physics problem just like this. And then it enters the second place where there's just an external magnetic field, and that's it. And then the particle will start turning and will hit the plate at a location that's determined by its mass. The mass of the particle will determine what is the radius of curvature of this path. And without getting into too much detail, this is what allows people to figure out what particles are shooting inside the detector. So this is how people figure out that the moon of Titan is made of methane. First, they shoot particles through this velocity selector. Now they know the speed of the particle. Now they use that speed in the second phase, and what they find is the mass of the particle. So they call that the mass spectrometer, and so on. Okay, anyway, I'm just showing you that this is very practical. It has a lot of applications, actually. Let's go back to the PowerPoint, though, not spend a lot of time. Okay, first, step number one. Did this agree with what we said? Absolutely. This is into the B field is into the board. There's some external magnetic field into the board. And the positive charge is going counterclockwise, just like we said, right? Notice that the size of the velocity vector does not change. The direction changes, but the speed does not change. Meaning, this, you see, in fact, it says so right here. It cannot change the speed of the particle. Why not? Because it doesn't do work. The B field does not do work. At this stage, later on, we'll see that there is a loophole. But right here, that's very clear. Based on our force formula, this cannot do work. It cannot change the kinetic energy of the particle. There's nothing it can do to change the kinetic energy of the particle. Okay. Okay, so now they're giving you more examples of that, and they're saying this has to do also with the northern lights, and these electrons are trapped in the magnetic field of the Earth. You know, I could discuss this a little bit, but not really. Let's get to the thing that I would like you to think about. Is more, I mean, this is kind of nice, of course. I do teach astronomy, and so this might gives me the temptation to get into it, but I'd rather avoid it at this point. Okay, so here they have the velocity selector I was telling you. In this case, they flip the plates with respect to what I show you. I had the positive plate on the left side, and here they have the positive plate on the right side. So that might throw you off. That's why the electric field here points to the left, because they flip the plates. And now they're also shooting a positive charge. I was shooting a negative charge, but it's the same thing. So they're trying to fight one force against the other. So if you manage to do that, and then you shoot at the right speed, then you can make this work. Okay. Okay, great. Let's do this instead. There is a part at the end of this PowerPoint that I'll just have to get to at the end. This part here is a little tricky. I'll have to spend a little bit of time on this. I'm not going to do this today. This is about torques. So now we have to remember how does it work with torques. So I'll definitely do that in the next class. This will be a little bit painful, but actually you can ask a lot of things about torques and loops, and forces and torques are not exactly the same thing, right? You should remember that from physics. So we'll get back to this in the next class. Let's just finish today with this point here. So far, we've been talking about charges moving in external magnetic fields, and then they put in one PowerPoint slide in there where they're telling you, oh, this is how I generate a magnetic field. Wow, let's just leave that for the next PowerPoint. Okay, so that's all that they just threw that in there. I don't like that. Okay, but in any case, right now, for this PowerPoint, let's just assume they never discuss how you're producing these external fields. There's a magnetic field everywhere, and then you're having moving charges. Okay, now in this step here, what they're trying to tell you is that if you have a moving charge, that's the same thing as a current. Okay? Now, they do something here I don't like, which is So it's the same thing as, so if you have a current, you know that it's a moving charge, and the direction of the current is in the direction of the flow of positive charges. We discussed that. That's a convention thing again. And then you can rewrite the force in terms of this of the wire and so on. And then you come up with this expression here. Let's just go right to the expression. Where I want you to notice something that bothers people a little bit, and I'll just finish with this for today. That's it. I'll do the torque stuff in the next class. That's a little bit of a headache, actually, because again, it's 3D, and you know that's always a problem drawing 3D drawings. I always prefer to do 2D drawings and then in and out of the board, just because I don't do very good drawings. So I'm probably going to stick with that approach, which is just keep doing 2D. And then you have to always keep in mind that I'm doing in and out as well. So that's 3D then. But in any case, last point here. And please notice this, because later on you'll come up with the same thing. When you come up with a force for a wire, now you have the current in the wire, and then they have L for the length of the wire. And then cross the B field. The external B field. So it's kind of weird, because if you pay a little bit of attention to that, what they did is they turned the wire itself into a vector. So that's why they do little l. L is the length of the wire. So they do L, and then they put a vector over top, meaning they just turn the wire into a vector. I think that's fine, you know, it doesn't matter, but it's more pleasing to me anyway. And many people do the same thing. Instead of writing the little l as the vector, it's nicer to write the current as a vector. The current, you know, the current could be this way, that way, the other way. I mean, that's pretty easy. I don't know, it's just a matter of taste. So I prefer to write the same equation with I being the vector. The current is the vector. Okay, so you just pick the direction of the current, and then you cross that with a B field, and then that's the force on the wire. Okay. Now, this is a force with directions. So for instance, okay, let's, last example, based on this, let's write this down, or let's write it in my form. I'll go to the other PowerPoint again. Okay. Let's see, let's not keep doing, let's do this one again. Since I don't wanna. Okay, so let's, let me write it down. Again, I'm doing it my way. It's the same thing as their way. I just like to say I is the vector, not L. Okay, so I have I cross B. So I have to put my fingers in the direction of the current, and then cross it into the B field, and then figure out the direction of the force. Okay, so here's the problem. I had it jotted down there, so this will be also from Master in Physics type problem. So suppose I have an external magnetic field, as usual, as always, and then I have this, and I'm going to say the current is in that direction. Okay? And then I have that, and then I have this. Okay? And then I ask for each piece, so the current goes here like that, and then the current goes there like that. So for each piece, I want you to tell me what is the force for that piece. Well, you will have to say how much of the wire is in the magnetic field. So of course, you have to know the length of the wire that's inside the magnetic field. By the way, there was a lab just like this, actually. As usual, I have no idea what they're doing for this, but we had a lab that was very easy. You just put magnets, and then you put wires, and you look at the wires around, and you stack them in the magnets. And then you use the scale to measure forces and figure out that this law is just, you rework this law experimentally. But in any case, so let's take by pieces. Piece one, so then there's piece two and piece three. So piece one here. And then that's it. I'm done. After that, how are we doing with that? Yes, right after this, I'm done. So there's piece one here, then 2 and 3. Well, 2 and 3, 1 and 3 are the same. So 1 and 2, how about 1 and 2? So on that piece of the wire 1, in what direction is the force on the wire? Up, down, left, or right, or 0. That's the other option. Here is the force. Again, I did the current in that direction. So what direction is the force? Up, correct. So 1 is up, right? So again, I'm going to the right, then I'm going into the board, to the right, into the board, my finger is up. Now, again, current, I don't have to worry about negative, there is no, I'm picking so there is no positive charge. Current is the flow of positive charges. So I don't have to worry about the sign of it. I'm already putting the sign of the current. Current, B field, thumb. So 1 would be up, then the other one would be current, B field to the left. So 2 left, and then 3 would be up again. Okay, so suppose I asked you, or I think Master in Physics asked something like this, what is the total net force on the wire? You couldn't just calculate the force on 1, add the force on 2, and add the force on 3. That wouldn't work. These are vectors, right? So 1 would be up, 1 to the left. So if you wanted to find the net force, you would have to do components. Fx squared plus fy squared square root. Okay, so you would have to start doing how much length each piece has, and so on. Okay, so that's kind of an interesting, not so super hard, but interesting problem. Okay, that's it. That's it for today. Again, next class, I will continue like this. This needs practice. So for this particular chapter, maybe what can help is to actually spend quite a bit of time on mastering physics. Make sure that that you ace it all, and then you get every question correct, and then that will make you practice these right-hand rules a lot, and then you'll get used to it, and you won't have to think about it at all. Okay, that's it for today. See you guys. Unless you have any questions, sorry. If you have any questions, great. Otherwise, that's it. Okay?
I had a quick question about the announcement. I had that you sent out like earlier this week. You said something about the average of the math and physics was
106 points. So what that means is that the average of the class through chapter 26 was 106 points.
Out of how many?
Out of well, what matters more is the class average. So you measure, but it was out of 150, something like that.
Oh, okay. I thought it was 106% at first, and I was like, oh, okay.
No. Oh, I see. No. So I think you have more than 106. So that would be weird, right? Because it would be more than 100%.
I was just, yeah, I know. I was just confused about what you meant.
You're doing well, I think. So that's, it's comparison between you and the class is just to show that you're keeping pace. That's pretty much it.
Okay, thanks.
Okay, see you.